In this lesson, we're going to talk about the rock cycle. We're going to look at the 3 different main kinds of rocks and how they turn into one another, how they change. So our 3 major rock groups are igneous, metamorphic, and sedimentary. Our igneous rocks come from molten rock from the mantle. They can either be intrusive or extrusive, and we'll talk a little bit more about what that means in a minute. We've got sedimentary rocks. We've got 2 different kinds of sedimentary rocks based on what kind of materials they're made out of. They're formed at Earth's surface, so they're not volcanic in nature. They're not coming from magma. We've got clastic sedimentary rocks, which are little bits and pieces of existing rock that gets broken down over time. And then we have chemical sedimentary rocks, which are made from the dissolved minerals that came out of other rocks. And then we have metamorphic rocks, and all rocks can turn into metamorphic rocks, and metamorphic rocks can turn into new metamorphic rocks, as long as they're exposed to heat and pressure. So, you have a diagram, you should have a handout, and you should have a line that shows where the ground is at, where the ground level is at, and you've got your magma chamber that's down at the bottom. So that's where we're going to start. When you are practicing with the rock cycle, it's always a good idea to start in the same place all the time as you're practicing, and that way you get used to the pattern of it. This is one of those concepts that you are going to want to practice because it is one of the questions that's on the written final exam. So we've got our magma. Magma is the molten rock that is below the surface. If our magma cools and crystallizes underneath the ground, it becomes an intrusive igneous rock. Intrusive for inside the earth. So we've got magma that started to move up, but it didn't get all the way up to the surface. Didn't feed into a magma chamber and become part of a volcano. It just moved up a little bit, and then it started to cool and became a chunk of rock. So a lot of times they turn into granite. It's one of the very common intrusive igneous rocks. You'll see when you look at granite, if you look at it closely, like you look at the granite countertop and think about how you can see all the different little chunks of stuff and their different colors and things like that. That's because it cooled over a long, long period of time. And it allowed the crystals to grow inside the rock. When the magma erupts out of the volcano and becomes lava, it doesn't have as much time for those crystals to form, and so we don't see individual crystals in our extrusive igneous rocks, or those ones that they exited the earth. Okay, so our pumice, like that stuff that they use for getting the calluses off of feet, that stone, that kind of thing, it floats in water. It's really light. There was a lot of gases and air that moved through it as it was formed. Obsidian is another example of an extrusive igneous rock that cooled really quickly. It's that volcanic glass, and the Native Americans used it for making arrowheads because the bonds between the molecules in the rock were so tight that it made the rock really hard and it made it really sharp. So extrusive rocks form outside of the surface of Earth, intrusive rocks form inside the surface of the Earth. In order for our next stage to happen, our intrusive rocks have to get uplifted out of the crust, and so that they're sitting and they're exposed to our elements. Our agents of erosion, once again, are gravity, wind, water, glaciers, and living things, right? So we have to expose the rocks to the weathering process, that breaking them down into the smaller pieces, and those pieces are called sediments. We can have physical sediments that came from our mechanical weathering, that is just the smaller chunks of the bigger piece of rock. We can also have chemical weathering and chemical sediments that come from the rocks being dissolved, like our limestone, with the water dissolving away the limestone. When it fizzes, and we talked about that before, when it fizzes and the chemicals are actually coming out of that rock, and then it gets washed away with water, and those become chemical sediments that can then become another kind of rock. So all those sediments have to move, right? So they're moving downhill. We talked about that too, about how gravity is pulling everything downhill. Erosion is that transport or that movement. And then they're going to stop moving at a certain place, and that's called deposition. And that's what we're looking at here. These are sediments that have been deposited. So these are physical sediments. It's sand that's been deposited over time. Now, if it sits there for long enough, and you get more and more sand that's piled on top and on top of one another, it's going to compact the sand and it's going to squish all those particles together, and it's going to squeeze out a lot of the water that's in between those particles, and it's going to make the size of the pores, the spaces in between the particles, it's going to make them really small. And what that allows to happen is, as water slowly now percolates through, the water that has those chemical sediments in it are going to act like glue. So we've got to squeeze the air out, we've got to squeeze all that other water out, and then we've got to stick it together with those chemical sediments in order for it to become a sedimentary rock. And so this is one example of a sedimentary rock. It's a conglomerate, which means basically that it had big physical chunks that are in a matrix of smaller sediments in here. So it's kind of like this was probably either the end or the side of a glacier, or it was in a stream bank, one or the other. Most likely it was in a stream bank, and these were the things that were the rocks that were tumbled down in the stream bed, and then the stream bed dried up, and the sediments built up on top of it and squished it down and made it into a rock. These are ripple marks. These are the preserved remains from mud. So this is mud that dried out over time. And then when the water goes out, like if you're in like at the beach or if you're at a lake or something like that, as the water moves out across the sediments, it causes these waves in the sediment itself, in the sand or in the mud. And then if the lake dries up and nothing is there to actually disturb it, then these can be preserved for a long time. And so that's how this kind of rock forms. These are mud cracks. So this is an area where the water has dried up, and those can also get preserved over time. They don't have a picture, but they can get preserved over time, and usually what you'll see is the mud that filled in the spaces is what's left behind, and then you can see those mud cracks. And we'll talk about that a little bit next semester when we're looking at geologic time. Now, our sedimentary rocks or igneous rocks, if they're buried, it increases the temperature and the pressure, which is the P is pressure and the T is temperature. It increases those, and it allows the molecules within the rock to actually kind of move around, and it makes a new rock. A metamorphic rock may have some characteristics that are similar to the parent rock, but for the most part, it becomes a new rock when it becomes metamorphic. And then if that gets pushed down even further, it will become magma again. What you're looking in here is an igneous rock that probably had a parent rock that was like diorite or granite or something like that. And as it got compressed and pushed over time, this rock got all folded up because these lines were once straight, just so you know. They would have been straight at one point in time, and so it's gotten all folded up, and the heat and pressure allowed some of the crystals to go towards one another and make these bands or these striping. It's called a foliated metamorphic rock, or a striped or banded metamorphic rock. The rocks get pushed down even further, they melt back down into magma. Now, we've drawn this in one nice little neat circle, but it doesn't necessarily always happen this way because we can have lots of shortcuts that can occur throughout the course of the rock cycle. So we can have our sedimentary rocks can get broken back down, back into sediments, and they can go back through the process again and become new sedimentary rocks. Metamorphic rocks can get broken down and become sediment. We can have igneous rocks that get pushed back down and go through the melting process, or go through heat and pressure and become metamorphic rocks. So we've got lots of different shortcuts within that system. So the rock cycle is one of the cycles that happens on our planet that redistributes the materials on our planet. So you'll see up here, this is our middle one. This is another representation of the rock cycle. The water cycle is part of that because it distributes the materials as they go along. And when you look at how does the rock cycle go along with plate tectonics, we're going to talk about that in the next chapter. But that heat and pressure gets applied as rocks get pushed down or subducted. The crust is getting pushed back down towards the mantle, and it adds that added pressure, and it can create our metamorphic rocks. And as more rocks get pushed down, they get melted, and that's how the rocks kind of move around. Because we look at the ground and we're like, it's not moving, but it is really moving very slowly over time. So it's all powered by the heat of the interior of the Earth, and we're going to talk about that a little bit in our plate tectonics unit as well. So here's one last look at our diagram. If you need to fill in parts on your diagram, go ahead and pause your video so that you can make sure that you got all the parts on your diagram completed.